Anything now?
Yeah, that's great. We can see the slides now.
Okay, that mode will work then. All right. So I'd like to lead off with just a little bit of taunting. So yeah, I got a web browser. It's called Firetran, and it renders HTML 10% faster than any of the existing browsers. Pretty cool, you say, right? But only if there's no JavaScript. Use JavaScript, you got to recompile. No big deal. The character encoding, the proxy configuration, it's all compiled in. That makes it faster. Mutually incompatible forks. I mean, everybody needs a customized version of their browser, right? There's no confusing runtime proxy dialogues. You just edit a file and recompile. For security, you can't mix HTTP and HTTPS, right? There's a lot of security vulnerabilities from doing that. All right, we got to compile it in separately. To load a page, you put the address in a configuration file and you run the executable, you get the page rendered. There's a tickle script that manages the configuration file, and we have plans to extend this script, recompile Firetran with optimal features for every page. It's open source, but the development is in private. So that probably sounds familiar. Firetran, of course, struggles with market share, right? This is the kind of the status quo in a lot of scientific software packages. It was more so 5 years ago when I sort of created this parody, but it's still pretty widespread. Why do we tolerate it? Is there something fundamentally different about scientific software? And I'm going to argue, no, there really shouldn't be something that's that different. We shouldn't have these really like different strategies for dealing with scientific software and for addressing performance in scientific software. I'm going to look at one other facet, and then I'll sort of return. So a few years ago, everybody was saying the future is all GPUs. And now a machine with no GPUs is the top in every one of the benchmarks, and was recently #1 in the Green 500. Now it's sitting at #4. This, of course, is the Fugaku machine. So the conventional wisdom is often not right. And sort of related aspect, so in the US, there's this project, now it's called E3SM, used to be called ACME. It's the climate modeling project the DOE runs. And in the original proposal, which was back in 2014, there was one performance requirement, well, only one objective at all. And it said minimize simulated years per wall clock day. And it said the target is 5 simulated years per wall clock day at the target resolution. It turns out that was never achieved. Back at the time, I said no DOE facility through 2020 will run ACME faster than Edison. And that remains true today. These figures are from 2019, using an entirely new rewritten dynamical core. We see on the left here, there's kind of a measure of efficiency, like a throughput per node. And on the x-axis, we've got number of compute nodes. And so we see towards the right end of this plot, this is the strong scaling limit. And the non-CPU architectures, and they actually have some GPU results as well, though not shown in this paper. And none of them are really outperforming this green line here, which was performance on Edison. And the same kind of thing if you show this is simulated year per day, still a strong scaling study. As we increase number of nodes, the green line here is pretty spot on straight. The blue line represents the pure CPU part of Cori that is based on Haswell. And so it is a faster CPU, but they don't have as many nodes as they had on Edison, and so it doesn't actually surpass it in performance. So to this day, Edison was the fastest machine run by Oscar anyway. Since then, BER has been buying their own machines because the public access machines that that Oscar runs deliver performance regressions on the single quantity of interest, this simulated year per wall clock day. So one of the fundamental reasons for this is that latency and throughput are really different quantities. So this is a figure just annotated from this 2019 paper. It's a good implementation of a particular multi-grid algorithm for high order elements. And we see the performance on Broadwell, and this is so here it's running on kind of an equivalent amount of hardware on the 3 different architectures. And so we see that our kind of classical CPU approach delivers high performance at faster time to solution than the more throughput-oriented architectures. These throughput-oriented architectures have high bandwidth memory, and so they do rise up to some high performance, though there's kind of a narrow window here because they don't have as much capacity of that high performance, of the high bandwidth memory. And so you have a reasonably narrow window here. If the problem is too big, then it may not fit in that device memory. And if the problem size is too small, then the inherent latency of using that architecture is higher, and going back to the pure CPU architecture beats it. And qualitatively, these kinds of results also hold on current generation. A little different look at this. This is just replotted data from a 2018 paper on near global climate simulation at 1 kilometer resolution. That paper was really arguing that this is the group at CSCS in Switzerland, and they were arguing that their completely rewritten version of Cosmo using GPUs was kind of the only strategy to get to 1 kilometer global resolution. The thing is, the 1 kilometer global resolution also comes with a simulated per day target, simulated year per day target. So I'm just going to replot this data, and I'm going to annotate here the left edge of these labels represents what would be needed to actually achieve that performance. And so we see the performance they got on the P100 and the less optimized performance that they got in their Haswell implementation. And this is really showing capability. So what we would like to be is way over to the left and way up high. We would like to be able to have like high throughput, high efficiency per node, and really fast execution time per time step. However, what we see is that there's really fundamental barriers. For each architecture, there's a barrier here. And weak scaling on this plot just stays in place. So you can see at different resolutions here, these are sort of weak scaled. And so you see you know, triangles and squares and such sitting on top of each other, basically. But in order to get out to 10 simulated years per day, for example, we have to be able to go over to the left. We don't just need the throughput. So I annotate this a little bit more. Here's the 5 simulated years per day, the 1 simulated year per day marks at 1 kilometer resolution. So this is where people are asking to get to. This is indeed a log scale over here. And I'm going to argue that moving to the left is really the fundamental problem. And that's where we need to be really careful about how we deal with our architectures. Moving up, it's just money. Yeah, money's hard to come by, but moving to the left is it's pure capability, even if you had infinite resources. And that never comes for free. And our new architectures have really not been reducing latency at all. They help quite a bit with throughput. So I call this a Pareto approach to capability. And I like to think about a few different objectives in this space. So first, the idea of a Pareto front is that you have multiple objectives, say F1 and F2 here. And what you would like is to, say, minimize both of those objectives. And what it means to be Pareto optimal is that to improve in one of the measures, you have to give up something in another. So C here is not Pareto optimal because you can improve in both measures at once, whereas the points that are marked along the front are Pareto optimal. And so we should really focus our attention on improving the Pareto front and not think too much about the points that are off of the Pareto front. The thing is, we got to take a holistic view about this. So there are a lot of factors that go into well, how we assess the models that we're looking at, the quality of their solution. Execution time, is that once it makes it through the queue, or is that the total workflow time that may include pre-processing, post-processing, maybe even implementation of new component models? The execution cost, so often this is measured in, say, node hours, because you get an allocation at a machine, and you have a budget of so many node hours that can be used by the end of the year. But maybe fundamentally, especially when we're comparing architectures, maybe we should think more about joules or about currency. And there's a human cost. So how much training is needed? What's the cognitive load? How do you build a community around that sort of product? Make it so that you can get contributions from the community that it can advance everybody's objectives. So one of the issues that we've had is that supercomputing facilities distort the economy quite a lot. And so to pick one example here, and I'll pick on Argonne because I was at Argonne at the time, they have this policy where most of the machine is only available for production, what they call production capability jobs. They have much longer time limits, so they can run for 24 hours instead of for 6 or 12 hours. And they have a higher priority in the queue. And so if you submit small jobs, then you're going to have to work with this smaller time limit. You may have to checkpoint more frequently. You got to break everything up into smaller pieces. There's quite a bit of cost to doing so. And so a bunch of people, including folks like Ray Loy at the facility, made this system to bundle runs together to improve the throughput. So they would take a bunch of jobs that were too small to qualify for the capability queue, right? It had to be more than 4,000 nodes to qualify for the capability queue. So they would bundle together a bunch of jobs that had no dependency on each other in order to get in the capability queue. They get higher priority, results faster. It seems better for everybody on the team, but it uses the resource less efficiently. And here's a whole bunch of authors on here from the project and at the facility that were just going around trying to game the queuing system. Why is there this incentive? Because they want to see big jobs that are actually using the machine. One of the reasons listed for purchasing Mira in the first place was climate, and the flagship climate simulation, even at high resolution, runs out of strong scaling before it fits in that capability queue. And so this is one example, but there's a lot of cases in which the incentives are from the funding agencies, from the facilities, are not really aligned with science and engineering objectives. There's a lot of incentive for PIs to just kind of play along with the game. And there is a cost to like getting allocations on different machines and figuring out, where's the most efficient way and the most efficient configuration to run something. Often it's easier to play the game, get a bigger allocation, and then you don't have to think about it as much. What I think is really interesting about cloud is it makes everything fungible. It all comes back to dollars or pounds. And so you can use whatever resource is appropriate. It also tends to incentivize things like containerized workflows, which make it easier in principle to move to different machines. And this fungibility, it also applies to human versus compute resources. And so it may be that, say, hiring another person to work on the project in order to do algorithmic development or otherwise improve the software may be a better use of resources than just continuing to run really large jobs, perhaps at lower efficiency. And if you get rid of the market distortion, then you can more efficiently allocate those resources. So let's think a little bit about human time. So the first thing, the one that users complain about all the time but developers underestimate, is packaging and distribution. If it isn't tested, you better believe it doesn't work. And so our kind of successful community projects often have a bunch of configurations that they run. Petsy builds like 60 configurations on every pipeline. The user experience is damaged even when it's the user's fault. So if they have a broken environment, they're going to try to build. They're going to say, Petsy doesn't build. Turns out, like, the C compiler doesn't work, but they don't know that. If they email us, maybe we can work it out, but that's maintainer time. Being able to use package managers, I think, is really important. Those things like apt, RPM, brew, this helps a lot for people getting going on their own machines. They're not popular on HPC machines, but having a way to easily get things installed, and especially if you work on libraries where there's, say, various higher level libraries that depend on it, then being able to be packaged is an important thing. Now, historically, upstream developers usually haven't been all that active in developing or maintaining their packages. And to some extent, SPAC changes that calculus a little bit. At least among the projects that I'm familiar with, often there are people from upstream that are maintaining the SPAC packages. And that may be every bit as much of a value as SPAC itself as an installation mode, just to make developers go through, how do you make a reliable, non-interactive install? So users build once per machine, and if it takes hours to build, that's an incentive to not want to build that very often, to not want to try out that environment. But developers build continuously, and developers don't build just on one architecture, on one project. They build on lots of projects, constantly switching between projects. And so having a way to build fast, especially to have fast incremental builds, is, I think, actually a really important part of building a community around software and getting people to really use it. And so there's techniques that help that a lot. Stable binary interfaces mean that you can do library development and not have to rebuild all the clients every time you want to test it. There are language features that hurt build performance quite a bit. This bottom item here is actually maybe the most interesting. Let's push more things off to runtime, do more things in runtime configuration. That helps a lot for packaging. It also means you don't have to recompile nearly as often. If it can be runtime, it really ought to be runtime. So we should be very selective about where we really need to compile something in. This quote from Matthew Turk, so the distinction between users and developers is actively harmful. One of the interesting things that we can do when we're designing libraries and other types of software is we can design them in a way that tricks users into becoming developers. So users are trying to get their work done. They're writing code for themselves. We want them to do that in a way that it's really tempting to contribute back. That they're not making local modifications, that they're just sort of creating forks, but rather they're implementing plugins, something of that sort, that's convenient to contribute back. And there's a lot of obstacles, and this is mostly a kind of quality of software development. But as a developer of a package, of a library or a modular application, we can design for debuggability. We can design for this extension to not have too many external dependencies, to be easily testable in ways that the user gets their work done, and either for altruism or because they realize, you know, if you get it into that library, you put your pipeline preload method into Petsy, then a bunch of people are going to use it because it's just going to be there. They won't have to install software. They're going to just go, you know, hey, what happens if I add this runtime flag? This aspect of design, I think, is something to think about really upfront. How are you going to recruit new developers, get people to transfer over? So we also really want to build communities. And so there's a bunch of ways in which we can model our communication, our review process, the infrastructure, to be able to foster a community, to make it so that people like to interact with that group so they can start contributing reviews, say, once they're you have the experience to do so. In the scientific space, we really don't have the resources to deal with lots of forks or maintaining different variants of packages. So major tech companies have done that. Often kind of famously underestimated the cost of forking and paid it off. Sometimes they've forked in order to take control of a project. I like to think that in science, we can be more collegial and work together in the vast majority of cases. But all of this, it kind of, it does depend a lot on maintainer time as well. So that there's a lot of aspects to building an effective community. And I guess finally on this facet, are we building applications? Are we building frameworks? Are we building libraries? So a lot of people say, well, we have an end user application. I'm the top of the stack. And yet, in reality, we have engineers scripting mouse clicks around commercial GUIs. You don't put AMR in your application, you put your application into AMR. This is sort of classic framework sort of speak. And the thing is, basically all the models that we build, there is a layer that goes around it. You might not have thought about it at the time when you were building that part, but uncertainty quantification, optimization, integration in products that matter to the end user, they tend to always wrap higher level aspects around it. And so we really need to concede that we don't control the whole environment. We are, even if we seem to be writing applications, it's not really the application. We need a programmatic interface. For some applications, yeah, we also really care about the interactive user interface, but there should always be a programmatic interface because somebody's going to build a layer around it. So there's a number of ways in which a focus on performance breaks this ecosystem, breaks the ability to wrap things around it, breaks the ability to use good methods. People say, oh, well, implicit solvers don't scale, and then they run diffusion explicitly. And this was actually a Gordon Bell talk a few years back. So it's important for us to to recognize when something is not worth it for performance. When it doesn't actually, maybe it significantly hurts our performance. And much of this requires understanding the problem domain enough to choose appropriate granularity, to minimize the scope at which we have to do, say, architecture-specific things or other kinds of optimizations. And as a strategy for really improving performance, I think we really need a better way to compete. We need to make competitions fun at various levels of abstraction. So in this Donahoe quote, the common task framework is basically the competitions like the Netflix challenge and other machine learning sort of challenges. This has really driven the field forward. And so what's our secret sauce here? So for vendors, we have benchmark suites. Those go into procurements. Usually the algorithm is fixed. Sometimes they can edit the code, sometimes not. When it's part of an acceptance test, vendors really work on it. You want to feature an MPI to work well, make it be part of the test. But for developers, we'd like to be able to have more creativity, but when we create tests that are too domain specific, then it's hard for people to participate. There's kind of too much background knowledge that needs to be picked up. And so Jeff talked about the parallel research kernels. I'm going to talk a little bit about the seed bake-off problems, some other examples in optimization, albeit not particularly large-scale optimization. There's this suite of test problems. There's also some ODE solver suites. And then all of those, like the algebraic problem that's meant to be solved has been stated. So it's kind of a discrete problem, maybe with over continuous variables, but it's a discrete problem. A verification challenge is expressed as a continuous problem. And so this allows us to do things like changing discretizations and playing all sorts of other tricks at that level. And then validation challenges are where all we have is data. We have an experimental setup. There's a CFD challenge that's going on right now that's sort of of this type. Take something that's hard to predict. So I'm going to turn to these seed BPs for a couple of slides here before I wrap up. And I want to talk about how to measure the performance. So we tend to have some kind of parameter. It's like an input parameter. It represents the problem size. It's how you choose number of elements or number of degrees of freedom. And there's an amount of work that goes along with that. It might be O of n with some constant. It might be n squared for some kinds of problems. And then there's an execution time. So how long does it take to run that fixed problem, problem of size n on P processors? We've got a rate at which the work is done. This is sometimes called throughput. and there's some sort of efficiency, rate of work per process. Or alternatively, we could normalize by cost. So what do we report? Well, lots of benchmarks report an Rmax. So this is just a maximum throughput. HPL is one of those, but lots of benchmarks do that. You get to configure the problem size to some extent in the way that you want. So often people will choose the biggest problem that fits in a given level of memory, and that allows us to hide latency. But as an end user, someone who really cares about getting results, that may not be the problem size that fits what it is that you want to do. And it doesn't speak anything to the kinds of, say, maximizing simulated year per day, like in the example much earlier. And so we've proposed a couple of metrics. 0.8 here is an arbitrary number. It's just like, many people would say it's acceptable to me to run at 80% efficiency if that gets me the, that gets me the answer faster. And so the n sub 0.8 is an architecture-dependent kind of characterization of what's an appropriate problem size. And so we've probably heard lots of, there's rules of thumb, like you should have at least 10,000. T sub 0.8 it allows us to compare different architectures. So we don't have to adjudicate what is a core, what is our granularity. Instead, this is just a practical measure of the minimum time that we can get our solution at an acceptable efficiency. And so let's take a look at what this may look like in practice. So I've got it on the left here. This is a measure of throughput versus time. And this is a measure of throughput also. So the y-axes are the same in both panels. And this is like n, so the problem size. And we can see here, this is very typical of higher order finite elements, that as you go to higher order, you actually get solutions much cheaper per degree of freedom. So we can move up here, going to second order, third, fourth. On the left, we see this time barrier. And so you can just kind of read off of this and you say, well, okay, at this is 100 milliseconds. So at 100 milliseconds, we can get 2.5 gigadofs. And we have a peak up here at, say, 3,500. And so you would read off from this, you would say, well, okay, well, a peak of 3,500, and we take 80% of that, and we're looking at over here, and it's an execution time of something like 120 milliseconds. And this allows us to compare from one machine to another. You can also see here, this is running on a CPU, and it's an AMD CPU. This two-socket system has 256 megabytes of level 3 cache, and you get 2.4 terabytes per second of bandwidth out of that level 3 cache. And so when you fit in level 3 cache, we get very high performance, and you spill out of that, and we start being limited by DRAM. Now, if you had a machine like Fugaku with high bandwidth memory, you would largely get rid of this drop. And we don't see this kind of drop if we switch over to GPUs. So this is an example on a GPU. However, on the GPU, we need a much larger problem size in order to get that the n sub 0.8. So the peak here should actually normalize to make it. Oops. So peak here is about 2 gigadofs for that benchmark. And over here, we see peak of about 2.5. However, at 1,000,000 degrees of freedom, they're about the same performance. CPU slightly ahead. And the GPU drops off a bit faster in this kind of small problem size domain. but we don't see it drop off over here. We just see eventually you run out of device memory. So these results were all produced with Lipseed. Lipseed is a finite element library without any finite elements. It just puts together the algebraic structure. It's meant to be really unintrusive so that existing packages can use it. And so we have different backends, and all of these, they work with a single source, and they're selectable at runtime. So there's some built-in, including vectorized backends. There's a one based on libxSMM, which is very popular in the spectral element world, and then more specific, backends for GPUs of various sorts. All of these use a single source, like vanilla C, to implement the physics, what goes on at quadrature points. And so that's the primary extension point, and then people compose on top of that. And it's available through MFEM, PETSI, and NEC 5000. MFEM has a bunch of different implementations, and Lipseed is the fastest in all of them right now. So this is an example of a library where we've kind of tried to condense out the really important bits and make it easy to use by higher level packages. Ideally, people developing those higher level packages the users of those higher level packages will perhaps not even know whether Lipseed is under the hood or not. So anyway, to wrap things up, the scientific software, the software engineering that goes into it really shouldn't be different from our other non-scientific software. We really have to focus on like how to make modular and extensible systems, make it possible to focus on algorithms before implementation. If we get too sucked into implementation, it stifles development of algorithms. There's a lot of interesting languages running around, and that makes this maybe a more challenging question than it was a few years ago. We have to think about packaging and distribution up front. And as a community, I would love to see us create more benchmarks that are accessible, that are not too complicated for creative new thinkers to jump in and make comparisons. The parallel research kernels and some of these other examples, I think, are good cases. And yet still bear in mind, the real world is messier than benchmarks. And so they won't take us all the way. Thanks. And perhaps I can take questions if there's time.
Thanks very much, Jed. So first question I've got is from Matt Nepley. Jeff has already given his answer, but I'll put it to you as well, Jed. So it's about your market analogy. And the question is, does the cloud have a good way of assigning a cost to latency? Meaning, is it possible for me to pay more and get something with a great network?
Absolutely, it's possible. So I think Azure is especially pushing that with their Cray partnership. But yeah, we have really competitive networks now in being shipped by the cloud providers.
Okay. Another question from Matt saying, shouldn't we also be reporting the accuracy improvement coming from incremental flops executed along the lines of your verification challenges?
Yes. So there's a couple ways to specify a verification challenge. And here it is. So the idea is you solve a continuous problem. I wrote here to a target accuracy, because the reality is people who are not mathematicians don't care about the asymptotic convergence rate. They care about what it takes to solve to a target accuracy. And that's something that they should think about a lot. How much accuracy do we need on this subcomponent of the problem? Because it doesn't make sense to oversolve one component where you have huge errors coming from another. We should try to balance those. You can write a different kind of of verification challenge, or especially you can make a trade-off curve. And these are really popular in the ODE community. Usually they're called work precision diagrams. But there you see a trade-off of execution cost versus accuracy. And so, yeah, as a reader of that sort of chart, you can say, well, I care about accuracy at the 10 to the minus 4 level, or I care about it at the 10 to the minus 8 level. And so you can read off like what constitutes a good method there. There's other ways to pose verification challenges, but I think for science and engineering purposes, competing at a target accuracy is actually pretty good, especially when we're looking at comparing different methods, perhaps as we scale the problem sizes.